So 97 start date. This is the aerial view of Jefferson Lab. So Jefferson Avenue along here on the road. So those hills that you see when you're driving by are the tops of the domes where our experimental halls are located. So our accelerator starts here. It's where our electrons are produced. It's all underground. It's a racetrack design. Electrons can go around as many as 5 times, and they're directed to one of our 3 experimental halls. And they set this place up so we could run all 3 at the same time in a pattern that goes 1, 2, 3, 1, 2, 3. So it's a machine running at 1.5 gigahertz. That's a big frequency, but everyone has computers, so you've heard gigahertz. And each hall receives 500 megahertz of beam. So we can do 3 experiments at the same time here from our accelerator. This is the cartoon view. First picture is making the electrons. So does anyone still have a CRT TV, the big, heavy TVs? Literally bent wire, run a current through it, you can liberate electrons, you can focus it with a cathode, put it on a screen, you can make a TV work. That's history. So just like only a few of you have that type of TV, we don't make electrons that way anymore. We use lasers. Yeah, lasers are cool. In fact, so Einstein didn't win Nobel Prize for E equals MC squared. Einstein won Nobel Prize for photoelectric effect. The idea that you can put laser light, put photons on a surface, and liberate electrons. So all the electrons that are liberated here at Jefferson Lab are done with a laser, shining on a material called strained gallium arsenide. That makes our beam, goes around a racetrack as many as 5 times, and then split off to our experimental halls. This photograph of our accelerator that pushes the electrons along, gives them energy, and our arcs that bend around. These are simple bending magnets, and these are our superconducting accelerators to give the beam energy. 6 billion electron volts is what we used to be able to deliver. We have just upgraded the machine. We just got approval to run. Actually, I had the Virginia governor here just a couple weeks ago. We can now get up to 12 billion electron volts. The reason we push in energy, the higher I go in energy, the smaller distance scale I can see. So if I want to see the very, very small, I need very, very high energies. That's why all the facilities, whether it's Jefferson Lab or CERN, when I want to see the very small, whether it's quarks and gluons or Higgs bosons, requires tremendous amount of energy. And this is the principle that drives that statement. Heisenberg, one of the old masters of quantum mechanics. So one formula only for tonight in my slides. Delta x, delta p greater than h bar over 2. Uncertainty in position times an uncertainty in momentum must be greater than h bar over 2. So tonight's just a number. 0.2 GeV times femtometer. What Heisenberg is talking about is it's impossible to know exactly the position and momentum of something at the same time. It's again a quantum mechanical idea, and one you're not used to, except in the way we are. Ever used a camera? If someone's running really fast and you take a picture with your camera, they look blurred in your photograph. So you know when you took the picture, where are they? They're blurred, they're spread out. So you know time, but you don't know position. If I use very high-speed film and photograph that same runner, they're stopped. There's no blur. Now I can't tell how fast they're going. Right? It's from the blur that you can tell when looking at a photograph, if you know the speed of the film, how fast they were moving. So there are examples in the classical world of the same uncertainty principle. And the camera is just a nice analogy. This is a fundamental limit. As far as we know, no way out. On the other hand, it explains why at Jefferson Lab we want to go to very high energies, so 10 billion electron volts or 10 GeV, lets me get down to see a small fraction of the size of a proton. It really lets me see what's inside. This is a cartoon of one set of our microscopes. We call them spectrometers. In this cartoon, we have people here. So this is in our experimental hall A. Electron beam in, put a target material in the center of our hall, and I can detect scattered electrons and scattered protons in these devices. This is what it looks like in real life. Cartoon, 2 microscopes, real life. A mess. But the target's still in the center room, and here's that spectrometer. It's the same device. Absolutely enormous. I need the really big to see the really small. I need very powerful magnets and detector systems. And this physically is what it takes. One thing that's great about this photograph is there's a big empty spot. And scientists love to build stuff for an empty spot. So back to the experiment. The idea they had in mind, send an electron beam in, detect a scattered electron, detect a scattered proton, and see what comes out. Does one thing come out? Lots of things come out. And that's where the point spot is, where the stuff would come out. When I see a proton coming out, when I see a neutron coming out, what would I see? The idea required building new equipment, shown in a cartoon. They wanted a new scattering chamber, someplace to put their target material, a bending magnet, simulator, and a neutron detector. To detect protons coming out or neutrons coming out. We gathered the magnet from Amsterdam. This is it sinking into the Dutch soil. We brought it here, recycled it. A group in Israel made particle detectors for us. A group in Glasgow made more of our detectors. University of Virginia built a scattering chamber for our particles, and Kent State provide neutron detectors. So for all the experiments we do here at the lab, it tends to be a community effort, an international effort, getting scientists here, building equipment, they'll set it up in an experimental hall. And this is what it looked like when it was all put together. So we have a bending. Neutrons have no charge, so they don't get bent by magnets. Would pass through a lead wall and be detected in this back detector. So they had a great experiment to do electron in, electron out, protons going forward, and see what comes back. Are they protons coming back, neutrons coming back, to try and learn something about when particles are close together. They started in '87. We approved in 2001. We finally ran. It only took a few months to actually run. We had 3 PhD students, one from MIT, one from Tel Aviv, one from Kent State, here in Newport News. They lived here for over 2 years analyzing that data. They start with the information of charged particles passing through matter and turn that into physics quantities, compare theory, write theses and papers. So finally getting all that done. 3 PhD theses, an article in the journal Science, a physical review letter, all written up about what we saw. And what we saw surprised a lot of people, surprised a lot of scientists. So we came in on carbon, electron in, electron out, proton forward, and what we saw was always a neutron coming back It was as if in carbon there were quasi-deuterons sitting there. The expectation was we'd see lots of proton-proton and neutron-neutron pairs. Real life was proton-neutron. That's why it was an exciting result. It wasn't what people expected. So it got a lot of press, and we tried to do a good job of explaining to others what we saw. And the importance beyond this cartoon of carbon with a proton-neutron close together, this actually has implications all the way up to a neutron star. And this is a cartoon of a naive picture of a neutron star. It's mostly neutrons. And naively you go, oh, there are a few protons, they're not going to matter. It's mostly going to be about a sea of neutrons. What our experiment said is no, the protons really want to pair up with neutrons. So in a system like a neutron star with only a few protons, they're not going to just be sitting there doing nothing. They're going to pair up. They're going to play a very important role in a neutron star. That's a paradigm shift. And to this day, this has become a very important result and has been reconfirmed several times. So, from beginning to end, about a decade. So we did an experiment where we learned a little bit about what happens inside a nucleus with protons and neutrons coming together. It has implications not only for nuclear physics, but astrophysics. I think that was pretty cool. But who cares? This is all basic research, and it's nice. It's nice figuring out what we're made out of. But is it worth all the time and energy and thought that goes into doing these experiments? Who cares? These are expensive experiments to do. So I'm going to give you a few examples of who cares. One, Kathy McCormick. She got her PhD here at Jefferson Lab and went to work for Homeland Security. This is a truck driving past something. Does anyone have a clue what that might be? It's a particle detector. Absolutely. If you want to know, in the trans containers that are coming through Hampton Roads through our shipping system, that there's no bombs, nuclear bombs, you need some way to detect it, and it better be fast. Because when you're working with business, time is money. Here's the idea. You put particle detectors that the truck has to drive by. At the same time, we're weighing the truck. We're either, if you do have a weapon in that truck, a nuclear weapon, we're either going to detect the radiation, because a nuclear weapon emits radiation that we can easily detect with the particle detectors we use here at Jefferson Lab, or you have shielded it with so much lead, your truck's going to be way overweight. Either way, when I know something's funny, stop the truck, inspect it. So Kathy McCormick cares about nuclear physics. Who else? Gordon Cates, professor at the University of Virginia. He was very interested in something called polarized helium-3. He wanted to study the neutron. Helium-3 has 2 protons, 1 neutron. We've known for a long time that the magnetic moment of helium-3 is very similar to the free neutron. So he's trying to learn about a free neutron using helium-3. He came up with a very clever way to polarize helium-3 so that neutron had a definite direction. Then he had a brilliant insight just talking to his friends. They were complaining about the inability of an MRI machine, magnetic resonance imaging, which is really nuclear magnetic resonance imaging, but they don't use the word nuclear at the hospital. Nuclear magnetic resonance imaging of the lungs. This is what a picture of your lungs looks like in an MRI machine. Has anyone sucked on helium gas from a balloon? Yeah, it's inert on that periodic table. It's on the inert side. What if you sucked in a little Gordon's polarized helium-3 gas and did the MRI? That's this picture. So Gordon came up with an idea. He was working with his friends. He was actually Princeton at the time, listening to people complain about their inability to do MRI of the lungs. Says, hey, I have polarized helium-3. Let's try it out. They literally tried it in a baggie and a straw, sucked some in, did the image, and pow, it worked. So Gordon cares. Who else cares? Tancredi Bono. This is one of my colleagues from when I was doing my PhD. He went to work for Schlumberger. Oil exploration. What the heck does oil exploration have to do with nuclear physics? How do you know where to drill? Schlumberger is a company, it's been around almost 100 years now. They tell people where to drill. What Schlumberger does, they drill exploratory holes. They then put a particle detector and a radioactive source down the hole, taking data the whole way down. They can tell you from the data exactly what the rock formations are all the way down the hole. So they're using particle detector techniques to map out, down over a mile, all the different rock formations. And when you're drilling for oil, you look for certain formations to know where to drill. So oil exploration also relies on nuclear physics. Thea Keppel cares. She works here at Jefferson Lab and was scientific director at the Proton Therapy Center here in Hampton. Inoperable tumors. How do we go after it? We have built here in Hampton Roads a proton accelerator, leveraging the resources and knowledge of people here at Jefferson Lab, as well as some very charismatic people at Hampton University, all got together. They built a proton accelerator here, and what's really cool about protons is they stop very suddenly. So if you have an inoperable brain tumor, I can put a beam of protons through your skull, through your brain, and have them stop on the tumor, leaving all the radiation right on the tumor. Thea cares. And this is just a huge windfall for Hampton Roads, world-class center. And finally, who else cares? And this is probably the oddest example of all. James Simmons cares. Last I checked, he was the 88th richest person in the world. James Simmons was the originator of quantitative finance. He took the techniques and skills, mathematics, etc., that we use here in our everyday research and applied it to finance. His original paper dates back from the late 60s. So his company is one of the first. What's amusing about his company, he will not hire you with an MBA. He doesn't want business majors. He only hires PhDs in math and science. Because he can teach anyone business, but he can't teach many people quantum mechanics or differential equations, Monte Carlo simulations, all the tools that we use and scientists just know a priori. He hires some of our best and brightest, they apply that to business, and I think that number speaks for itself. He's done extremely well at quantitative finance. So there's just a few examples. I tried to span the gambit of things beyond basic research that have come from Jefferson Lab. So, time to wake up and ask some questions. Thank you. Yeah, back.
What's the purpose of sending the electrons around the track 5 times?
Excellent question. So the reason we're sending the electrons around the track 5 times, and each time around they get more energy. So at a facility that came before us in California called SLAC, they took the electrons and they accelerated them down a mile through accelerator. And it turns out it's the accelerator pieces that are extremely expensive. So the clever idea they had for this facility is, let's bend the beam back around, and magnets to bend the beam around are cheap. So we accelerate, bend around, and they go right back through that same accelerator again to get even more energy. And it's all about money. I can put the accelerator in a smaller footprint, and it's just cheaper to build, and I get to the same energies. Yep.
Okay, going back to that, why is it limited to just 5 times?
What will limit you in the end, and actually we have basically hit the limit with our 12 GeV upgrade, as a charged particle gets bent around, it'll start emitting radiation, synchrotron radiation, and that grows very fast with energies. So eventually you'll hit, your radius is basically too tight. So it's almost like a race car at the racetrack. If we get to 200 miles per hour, 30 miles per hour, I just can't make the turn. So same idea, different situation. Yeah?
How long is exactly like the 4.5
Roughly a mile. If you start from the injector, go around and go into the hull. Yep. So in the hall, some of the domes are bigger than the others. So I only talked tonight about one of our experimental halls. They had 2 spectrometers. What I didn't mention is those 2 giant spectrometers can move. We can rotate them at an angle. So we need a huge room to be able to do that. And we have, that particular hall has the biggest dome. The hall immediately beside it has a very small dome. Their detector basically looked like a giant hollowed out egg. Nothing moved. So an enormous detector, but it fit in a smaller room because they didn't need to move anything. So those hills are really custom, or built above customized setups for each of the experimental halls. And the idea was different experiments needed different setups. In a very general level, Hall A was 2 microscopes that could move. Hall B had a static setup. In Hall C, we could build whatever you wanted.
You mentioned that when you're talking about funding, that most of the funding, all things you named, are federal agencies. Is there any private people that invest in this kind of research? Any private corporations?
So one of the biggest at the moment actually is the Simmons Foundation. So Gene Simmons, who was originally a math professor, then went into quantitative finance, has helped directly with the funding of our sister lab at Brookhaven. But probably the more important thing he's done is created the Simmons Foundation, which is providing a lot of money for something called the archive, where we as scientists put our work so it's publicly accessible. So yes, there are some private revenue streams. For our federal funding, I think what's most important is our international collaborations and the international money that comes here. Because it's really easy to raise your hand and say, I want money. It has a lot more weight if you also get the colleagues from Japan or Germany or anywhere around the world that also say, we want to do this and we're willing to contribute. That helps tremendously. And a lot of our big experiments, we built big international groups where they all bring in their manpower, their equipment, their money, come here to help get it done. Yeah.
With an electron turret, it was energy, correct?
Yes.
So why don't you just make it, like, just unfold it from, like, an oval, it's just a straight line, so it doesn't lose any energy, keeps accelerating and accelerating, and it hits the speed of light.
So the question was, why not just make it a straight line?
Yeah.
And you also mentioned speed of light, so I'll hit both. So our friends in California at SLAC did the straight line accelerator. It's more expensive. It's as simple as that. It's more expensive to make a long, straight accelerator than to make the oval setup. But you're right, they can get to a higher energy. They'll never have the limitation of the bend. It's a trade-off. The particles we accelerate here at Jefferson Lab, we take an electron, the smallest fundamental particles we know, and accelerate it as hard as we can. 12 billion electron volts. It's going 0.99999, the speed of light. Brute force, you can't get past the speed of light. We keep putting in more energy, it's still going the same speed. You never get exactly to the speed of light. Yep.
Well, we have to go through the writing so that we can see what happens. The old method detail. I want the part.
So it's very much so when we're doing an experiment here, it's very statistical. So I'm taking a foil of carbon, I'm putting the electron beam on it, and I'm looking at lots and lots of events so I can figure out what happens. So it's almost like playing a game of pool where someone's always setting the balls in the same place, and you're firing the cue ball in there, and you see where the balls come out, but you don't actually see the moment that it hits. I don't see that part, and that's actually makes nuclear physics really hard. I see what comes out. I have to figure out what happened. But you do enough experiments, if you watch the pool table, even if you never saw that rack of balls, you could figure out it was there by seeing where all the balls go when you fire in from different angles. Yep. Yes. So when Jefferson Lab is running, we have something called prompt radiation. It means there's radiation when our machine is on. There's radiation from the electrons bending. There's radiation from the electrons hitting a material. We turn our beam off, almost all the radiation is gone. With exceptions of the material I'm hitting where I've passed the beam through, it will still be activated and our dumps. So if you look carefully from Jefferson Avenue, you'll see little tails behind those domes. They have large vats of water at the end that catch the beam. We aren't in there when the beam is running. You know, and they're very careful to make sure no one's in there when the beam is running. So beam running, everyone's out. We have a key system to make sure no one is in. Yes. Yeah. So it'd be electromagnetic. So alphas and betas would be hitting a target material and knocking stuff out. Here in the back?
As I understand it, as something goes at the speed of light, it also increases in size. Starting off at this, by the time you get to 12 volts, or 12, whatever the number is, how much larger is it than this? Right?
I don't think large is the right way to look at it, but you can look at it as massive. Yeah. Mass. So electron in the units that we're using is half a mega electron volt. You can say half an MeV, and we're accelerating it to 12 GeV. So we put more energy in it than it weighs, which is an unbelievable amount. I mean, we've seen pictures of a nuclear explosion. We took some material and turned that material partially into energy. We take the electrons here. We've now put more energy into them than their mass. They're still not going faster than the speed of light. Now, whether you want to look at it as it gained mass, or it gained energy. It's two sides of the same coin, and quite frankly, it really depends on how you want to look at the information you're getting. Whether you want to think of it as a very massive thing coming in or a very energetic thing, it doesn't matter. E equals mc squared. Energy, mass, there's an equivalence there, so it's okay. Yeah?
When you run a machine, it emits radiation. So where does this radiation go in
so the question is, where does the radiation go when we're not using it anymore? So, for example, I said we turn the electron beam, it's making radiation, I turn it off, it's gone. So electrons going around the arc are emitting a lot of photons. They're being absorbed in the walls down in the hall. And as soon as you turn it off, all those photons are going into the light, bounce around, hit the walls, get absorbed, they're gone. It's going into heat. The same thing is going on when you go through the X-ray machine, or your bag goes through the X-ray machine at the airport. They're putting radiation on your bag. They're looking at what passes through, the X-rays passing through the bag and what's getting absorbed. Turn off the machine, it's off.
Or your microwave oven.
Microwave ovens.
What's a carbon card?
It's just a foil. I ordered it from a company called Goodfellows. They will send you a nice big sheet of carbon. We cut it down to a nice foil, put that foil in the beam so it's perpendicular, and run the beam straight through it. It's a very simple setup, and it's very easy to get homogeneous carbon, pure carbon. But the wall's made out of concrete. The wall's made out of concrete. Protons are getting rid of the tumors. So again, the idea is that radiation can damage cells. Right? That's kind of why we worry about getting exposed to radiation. It can damage cells, you can get a tumor. On the other hand, if I can put the radiation in a controlled way, so the proton therapy machine here in Hampton, very carefully, they would do an MRI. If you had a brain tumor that was inoperable, it means I can't operate to get it out. I'd do an MRI scan of your head. I'd locate exactly where the tumor is, and then I would put the protons exactly on the tumor. The technology to build a machine like this proton therapy machine has been around for decades. The problem was we didn't have the technology to make use of it. You really need an MRI machine. I need to be able to scan the brain and where the tumor is very precisely. I don't want to put the proton beam and have protons stopping on good tissue. I only want to know the bad. So I need an MRI, and I needed a computer. I needed a powerful computer really to control where I'm putting those protons. So it's really a clever trick. I'm going to put protons. I don't have them stop just on the tumor, just on the thing I want to kill. Because I can use radiation to kill the bad stuff too. So in this case, we're using radiation to do something good. Yep. Let's speak up. Oh, okay. Yep. So the question, if you had a proton machine in there, hitting you with protons, does radiation get in your body? A little bit, and there are trade-offs. So most of the energy from the proton will stop on the tumor, a little bit goes through your brain, and a little bit will get absorbed. The clever thing that they do when you go in for a brain tumor treatment, you come in one day, they send the beam in from your left side, next time from the right, and they come in at different angles, so they're not going through good tissue while maximizing the dose on the tumor, try to kill the tumor. Any small amount of radiation can harm you, so you want to keep it minimal, but very small amounts have been shown to do very little. In fact, we're getting it right now. You're always getting radiation. So the rate of radiation we get right now is called a millirem. We get roughly 365 millirem a year of radiation. And that's just part of being here on this planet. Radiation comes from our sun, hits our atmosphere, cascades down, and there are particles passing through us as we speak. So a square meter, so this table is 100 particles per second are going through this table right now. I can't see them, but they're there. So radiation is around us all the time. And that's one misconception people have about radiation. They just hear radiation and go bad without really learning about it, what it is, that it is around us. And there's a trade-off between medical applications of radiation. When you're at the dentist, you get a dental x-ray, look at your teeth. So you're getting a little bit of radiation, and the benefits of being able to see the cavities before they develop into something worse outweighs the risk of getting cancer from that little bit of radiation. So it's always a trade-off.
Just take a moment. Some of you may be getting ready to leave. Some of you may wish to stick around a little bit longer. I'll go ahead and open the door, or you can use the back door. If you need a piece of paper signed for school, we do have staff out front to take care of that. The rest of you are welcome to stay and continue after you done.
Okay, so if you have any more questions, just come on down. Thank you very much.
I'd like to welcome you all here to Jefferson Lab. My name is Joyce Miller, and I'm a mechanical designer. The captain of the Jefferson Lab Dog Training Club. So if you were wondering how we got this to Hampton.
Some time introducing cytotoxic T cells, which is failing, how can we improve upon that? And then we're going to move on to some mostly unpublished work from my lab, looking at ways in which infected cells themselves might be able to resist being killed by these killer T cells, and what might we be able to do about that to try to cure. HIV These are cryo-EM images of the virus itself, and then reconstructions of what a viral particle looks like in 3D. These are about 200 nanometers in diameter. And here's what you need to know about the HIV replication cycle for the purposes of this talk. So HIV is a cell-free virus. It binds to CD4, which is the receptor on CD4 T cells, and then also to a co-receptor. It has an RNA genome, which then is reverse transcribed into DNA. And something that's really important for this talk is to know that that DNA then actually inserts itself into our own genome, so our own DNA. And one of the questions we're going to ask is what kind of functional implications might that have on that cell that the virus integrates into. After that, we get transcription of HIV into RNA, which can then express proteins, and then we get the production of new virus particles, and the cycle repeats itself. So if we don't have antiretroviral medication, this is the course of infection in a typical infected individual. So in red, we have the viral load, so it spikes up in what we call acute or early infection, reaching often millions of copies per ml of blood. It then comes down to what we call a set point, so maybe tens of thousands of copies, a little bit lower, and stays there for some time. So this kind of looks like a bit of a détente maybe with the immune system. People aren't really symptomatic during this period, but we're progressively